All right. Here we go. Well, welcome to everyone in class. It's good to see you again. And to anybody watching, you are watching 5 Live Free Code School. We have 5 students live in the classroom with me. I'm Eric Gross, I'm the instructor. And anybody's free to watch and follow along with everything we do in class and also with the homework. I did update the Dropbox folder that has the homework in it. So for any of you who have any questions about that, just look at my socials right here on Twitch, and you'll see the link to 5 Live FAQ. And right in there is a link to the Dropbox. So you can actually find any of the assignments that the students have been doing. Which is where I kind of wanted to start with. I haven't reviewed every submission from last week, but I just want to call out a few specific things and then see if there were any questions. In particular, Sudesh's explanation of binary was excellent. Had a really great diagram showing, helping to illustrate it. Was pretty good. Jonas is in the middle of yours, written extremely well. I loved it. And I've got to get to everybody's, but the thing I noticed yet again is you all seem to have taken to heart the idea of being able to explain some of these concepts in a simple, clear manner. And I'm very, very heartened by it. It's fantastic. It's just, it'll serve you really, really well. And it shows that you understand it, because you can't explain things in a simple, clear manner if they're not simple and clear in your mind. Does anybody have any particular questions on either number systems or the Boolean comparisons that we put down, or the machine cycle? Anybody have any questions? It's still lingering from last week. Okay, cool, excellent. All right, today we're going to talk about two broad areas, and we'll go a little bit deep into each one. And I want to stress that what we're about to learn in terms of analog versus digital, and in terms of Boolean logic, is just enough to be able to equip you with the tools you need as a software developer. Each of these subjects you can go very, very deep on. There are an entire series of college classes on it. Some people make different aspects of this their life's work. There's a lot of depth here, but in terms of practical tools, there's just a few fundamental things you need to understand to help you as an engineer. So we're going to start out with this concept of analog and digital. We hear this word digital all the time. Can anybody give some kind of an explanation of what they think digital means?
Is it okay to use an explanation from your book?
1000%.
Distinct differences in states, conditions, or parts?
That is phenomenal. That's totally right. Can you or someone else give an example of something that is digital, that has distinct differences in states, conditions, or parts?
Like a digital clock, when it changes from numbers.
Yeah, okay, good. Good. Does anybody have any questions on Alexandra's explanation there? Okay. What does analog mean then?
There is a constant movement from, for example, with a speed car. You can see the needles going and it's never stopping at one point rather than another one.
Good. You guys are spot on. Okay, good. This is going to help. The fact that you already have some really good solid understanding of the concepts here. We're going to dive deep into each of these a little bit. In particular, we're going to dive deep enough to understand how it is that a computer will never be able to actually 100% contain something that represents the real world. We're never going to be able to model the real world perfectly inside a computer. At least the current technology that we have for computers nowadays. I don't know what things can be like in 100 years, but the way they are now, it turns out that we can get close to having some sort of a value in a computer that models a real world value or amount or thing, but we're never going to be capable of 100% representing that thing. But it also doesn't matter that we can't 100% represent it if we do our jobs as engineers. And so I want to dive into that and kind of explain what the heck that is that I'm talking about. I'm going to switch over to sharing my screen. And let me get this Zoom controls out of the way. So both of you, Alexandra and Ellen, brought up a couple of really, really good points here. I want to start from just the concept of what analog means. Can someone do, that's a highlighter. I don't want that at all. Let's go with a pen. Oh, my bracelet touched the screen and ruined everything. Can someone look up right now what the definition of analog as a noun is? Just look it up on Google or dictionary.com or something. Anybody got a noun for analog?
Mechanism or device in which information is represented by continuously variable physical quantities.
Hmm. Did I get that right?
Looks like
Okay.
it.
There's a couple of things I want to highlight here that we're going to talk about. Okay.
Oh, I think I gave you the meaning of analog and not just the noun definition. The noun definition is something that is analogous or similar to something else.
Good. Thank you.
Sorry.
No, this is good. I wanted both things here. So give me that again. Say that all out loud again.
Yeah, sure. The noun definition just says something that is I cannot say that word. Analogous or similar to something else.
I have another one.
Okay, hold on just a moment. What is that the definition for? What word? Is it analogy?
No, analog.
Analog. Good. Thank you.
That's what it says on Merriam-Webster.
Okay, and there's one more. We're going to use all of these. And again, I am heading somewhere relatively important with this. What's this other one?
A person or thing seen as comparable to another.
Oh, good. Okay, so there's a couple themes that we're seeing here. And that is that an analog is not the thing itself. Personal thing seen as comparable to another. So the analog is not the original thing. Analog, something that is analogous or similar to something else. Again, the analog is not the original thing. Here, a device that represents information. It isn't the information itself. So we're going to come back to this top one in some detail, but I want to start with a bit of an illustration. Let's just see Eric's phenomenal art skills. I know you're about to be extremely impressed. Yeah, don't say nothing. All right. Now, one thing that's been needed for a long time in cars, or sorry, that was needed early on, is we need to know what their speed is. Duh. And this is what Ellen was sort of referring to, the speed of a car, right? Now, we're talking up here about the actual thing, and then the analog is comparable to it. We're talking here in something that's analogous or similar to another thing. So, and then we're talking about a device that represents information. It's not the information itself. So this part, next part right here, conceptually, is actually pretty important. I have no doubt that any of you will be able to grasp this, but it's kind of important when it comes to computers. Let's ignore computers and machinery altogether and just think about something. This car is in fact moving at a specific speed. Let's say it happens to be moving at exactly 50 miles per hour. I apologize to Sudesh and to Jonas, who are probably used to kilometers per hour. Am I right?
Yes.
No, we do miles.
Oh, you do? What about you, Jonas?
We apply both.
Wow. Okay, good. Never mind. Take away KPH. Okay. But the point is, we actually have an actual speed. Like in the real world, that car happens to legitimately actually be moving at this speed. We don't really know that. And frankly, I don't really know a way that we can just know that happens to be how fast we're traveling. So what do? We create an analog. We create something that is analogous to something else. So what we create is a dial on them on the dashboard. We've all seen and it has a needle. That is not our speed. That's just a piece of machinery. But it is an analog. It is similar to something else. It represents something else. That part should probably be dead simple. Anybody have any questions on that? All right, now, without getting too deep into electronics, how do we make this thing over here work? How do we make the speedometer? How do we make it work?
Can we have a sensor around the wheels or the
let's see.
transmission?
I'm going to take a wheel. I'm going to try to give it a little bit of dimension. I'm not an artist. So here's a wheel. Now, let's say there's an axle coming out of the wheel, that goes into the wheel. And what if right on that axle, we had a fixed item, and that was a sensor. And what if, more precisely, on this part of the vehicle, the tire, that was in fact going roundy. That's a technical term, roundy. What if on the actual wheel itself, we had a little teeny magnet? Now, frankly, I don't know if this is the way they do it, and I don't care. The principle is the same. Someone who designs cars would probably want to reach through the computer and hit me in the face. But this sensor, what it does is it senses, let's see if I can actually do that. The magnet. And it produces electricity. And if you were to look at the output, let's say there's a wire going from the sensor. If you were to like put your eyes right on that and just look at it at any moment in time, then you would have plus voltage, minus voltage, here's 0. There would be some level of voltage out of it at all times. At any moment in time, it might be producing, say, let's say the positive here was 10 volts, and this is minus 10. At some moment in time, it might be right here at about 5. And then a little while later, it might be at 3. A little while later, it might be up to 9. And then we're coming to rest, it might be at 1. But the point is, at any split tiniest instant in time, it has some value. And that value can be anything between, say, whoa, that was a mistake. That value can be anything between 0 and 10. This electrical signal right here is what is analogous. That is and let's look at this again. Analogous, similar to something. It's similar to something real. What is it similar to that's real?
The motion.
Motion is similar to the actual speed. Remember, this electricity, this is not the speed. This is some electricity. The actual speed is what's really happening in the real world. The electrical signal, which might look like this, slowly going down, suddenly speeding up, dropping suddenly because we hit the brakes, steadily rising again. Oh, this new application, if you hold the signal down or that pencil down, it turns into a straight line. So that was a mistake. Let's draw that a little more quickly. It might look like this, like that. Over time, we're slowly rising. We might be hitting, say, might be approaching, say, 50 miles per hour up here, and then we suddenly drop to about 15 because we're approaching a stop sign, a stop light, but it turns green and we don't come all the way to 0, and we speed up quite a bit to just about 50 again. And then we have to slow down because there's a traffic jam. But then we're like, you know, I've got some open road and we go all the way to 65. This little graph is going to be kind of useful to us for something really important involving computers. If we go back, this, remember, is an electronic signal. It is being taken and it's being input, I'm going to use the green, right into the control mechanism for this needle. As the electronic signal changes, goes up, down, up, down, up. Literally, it's affecting a little teeny motor right here, and it's turning the needle. Probably none of this should be a surprise to you. Now is where we get really, really, really weirdly ugly. We're going to look at two things side by side. We have an analog speedometer. It has our 0, 10, 20, 30, 40, 50, 60, 70, 80, and you shouldn't be going any faster than that. I'm kidding. I would love to. And it has our red needle. I'm going to start with it right at 50. Now, over here, we got a whole different beast. We have a digital speedometer. Has anybody seen a digital speedometer in a car?
Yes.
Okay. Now, when we start our little thought experiment here, we are going to be at 50.0 miles per hour on both of them. Now, let's talk a little bit about how we can even have a digital readout. We have this signal above. This electronic signal, we can point it to both of these types of displays. With the one on the left, the way it works is pretty simple. That electricity literally is applied to this tiny little motor right here. And the amount of electricity is proportional to how far to the right does that needle move. The tiniest incremental change, if we were to expand this change right here in front of us and literally get down in there and go, okay, from right here to right here, inside those boundaries, how much does the voltage change? And let's say you got really, really nerdy and you found out that, well, it changes. Literally, it starts out at a voltage that means, I want to change that to black. Let's see, right there, it was 30.23 miles per hour. And then let's say at this spot, which is plus 0.5 seconds, it's only a half a second later. Let's say this spot right here, the second one, this was 30.8176 miles per hour. Now remember, we're talking about electricity. There's no computer involved here. It's just a certain amount of voltage. But remember that this signal is an analogy to the real world. And in the real world, the exact voltage right at those two instants in time, the first one means the car was actually going 30.23 miles an hour at that exact second, that exact split instant. And then a half a second later, the car was actually for real in the real world going exactly 30.8176 miles per hour. That is actually pretty dang easy to represent on this analog speedometer. You couldn't see maybe with the naked eye that kind of a change from 30.23 to 30.81. I don't know if you could see it that much, but the needle would move. The needle would move. Now, let's look over here to the digital. We're going to take this self-same electronic signal and shove it into a digital display. How do we make that work? Any questions? Any ideas about how we might make that work?
Would it be with like binary, like the 0 and 1s?
Yes, ultimately. And that is exactly where we're heading. Our destination is in this 0 and 1 thing, okay? Let's give it a little bit more abstract, like kind of a concept first, before we get down to like literally 0s and 1s. Here's a bit more of an abstract concept. Let's make this a little bit larger. And we're going to say that this digital machine, this digital speedometer needs a thing called an analog / digital converter. It is a machine, electronic circuit, that takes in a varying analog signal. That's electricity, plus, minus, it's electricity. And it puts out a digital signal. Now, we need to explore, what does that digital signal mean? It's because of the work that we all did over the last 2 sessions that we can start to think with some of the concepts here. What this circuit right here is actually going to do is, just like a computer, it has a clock. The clock inside it operates just like we were talking about last week. What it does is, every single time it has a signal, it goes up, it goes up, it goes up. Just like we were talking about with a computer. Every time that happens, it samples the actual electricity that it's receiving. And it does it very fast, one after the other, after the other, because it's trying to get as close as it can to what the input is. But let's just take one exact instance, and we're going to blow this up a little bit. We're going to say that here's our analog to digital. See, black. Here is this analog to digital converter. And let's look at the signal going into it. And let's specifically look, if we think that it like changes a lot, like this, we're going to take one specific spot on it. Let's say we're going to choose this little area right here, and we're going to examine it. So let's blow that up a little bit. Let's say that that looks like, and try to reproduce it. This is where it goes in. What was that? That was a mistake. This green thing, this is the input. And then let's go back to black. This is the actual electrical signal that's being fed into it. It goes down and then up a little bit. That's what I was trying to reproduce right here. So you see that signal. Let's expand that and make it quite large. It's bigger now. Good. Now, let's say that this analog to digital converter is operating at such a speed that it can sample this spot right here, this spot right here, this one, this one, this one, like that. Like that might be every 3 milliseconds. It might be every like 1/1000th of a millisecond. Like it's trying to do is to measure it as quick as often as possible. But let's just say it measures it there. And then let's further say that in the real world, this bottom spot right here, this one right here, this happens to be a voltage level that is equivalent to exactly 50 miles per hour. And then let's say this one to the left right here is exactly, because it's a tiny bit higher, it's 50.1 miles per hour. And the first one is 50.6 miles per hour. All right. So we're going to start here on the left, because even though we've sort of drawn it, we've drawn it the way we have, we think about how this thing's going to be processed. This is over time. Time is moving this way. So let's say we start our analysis of how this analog to digital converter works right at this exact instant in time. What that means is the clock right here went click, and the analog to digital converter said, okay, let me look at the incoming signal. Oh, it is 50.6 miles per hour worth of voltage. Now, let's say that the output right over here can only have whole numbers. That's just how it was physically constructed. This particular analog to digital converter can only put out a voltage that represents a whole number. If we have 50.6 going into it, what would come out of it? A voltage representing what number? 50 or 51?
51.
Yeah, let's say we built it to round up. So the output, the first one is, we'll start drawing it down here. Whoa, I don't know what that happened right there. Okay. The first output is this little dot right here, and it's 51 miles per hour. All right. Another couple of milliseconds or a tiny fraction of time goes by, and the clock says, hey, sample the input again. It looks, the analog to digital converter is utterly unaware of what this electronic signal that's going into it was doing between the first sample and the second one. It has no idea what the voltage was. As far as it is concerned, for that period of time when it wasn't paying attention, the voltage could have spiked up to be 200 miles per hour equivalent. It doesn't know. It could have dropped to 0. It doesn't know because it wasn't looking. It wasn't sampling. But now, some tiniest fraction of a second later, it does happen to sample because the clock said, hey, analog to digital converter, please sample. It looks and it sees a voltage that's equivalent to 50.1 miles per hour. It says, oh, let me convert that to a digit. And the output can only be in whole numbers for this machine. That's the way that people made it. It can only output whole numbers. So it outputs a voltage. What voltage, or sorry, what mile per hour is that voltage equivalent to?
$50.
Exactly. So the next one is, oh, sorry, went the wrong way. It's down a little bit. 50 miles per hour. Okay. Now, a split second later, we hit another clock signal. The analog to digital converter says, oh, now I need to sample the incoming signal. It looks, and it's this third one right here. It's exactly 50 miles per hour. I said gallon. That's funny. The voltage coming in is exactly 50 miles per hour. Well, that's pretty simple. We'll put out 50 miles per hour. Now, before we go any farther, I want to point something out. The first of those two 50s that came out of this analog to digital converter was a lie. The speed of the car at that exact instant in time was not, in fact, 50 miles per hour. It was 50.1 miles per hour. But we made this analog to digital converter such that the precision it's capable of is only to whole numbers. So we had to make a call. What do we represent it as? This brings up the actual definition of digital better than anything, I think. So Alexandra, can you read that again? Or you may have just spat it out word for word because you're a nerd and memorized it. But can you read digital again from when we first started this discussion?
Yeah, distinct differences in states, conditions, or parts.
Good. It's a lot of D's. One other characteristic of digital is that it represents quantities or data using discrete numbers. Can someone look up the word discrete for me?
Individually separate and distinct.
Good. So if we design a digital system, it needs to represent quantities or data using discrete numbers, meaning they're individually separate and distinct. This means that we either, for example, can have a number of 50 We can have a number of 51. We cannot have anything in between. There's not 50-ish or 51-ish. If we've decided that the greatest precision is a whole number, then we must represent quantities using distinct values that stop at the whole number. We cannot go farther in a digital system. Now, we could build this entire thing, this analog to digital converter, such that it would allow, there's a decimal point, tenths. The accuracy could be to the nearest 1/10. But now, does that solve our problem? We could have 50.4 miles per hour. Sorry. 50.6 miles per hour on the first one, and 50.1 on the second, and then slightly down a little bit to 50.0. But let's just look at this for a second. Do you think that this first number, the speed is actually exactly 50.60000 repeating miles per hour? I mean, in the real world, do you think that we captured the speed of that car at some precise exact instant where the speed was literally exactly 50.6, full stop, that's it? It was neither less than or greater than 50.6 to even the slightest degree. Does anybody think that we actually did that? Or that it's even possible that it occurred at all?
In my
Could something be
opinion,
going exactly 50.6 miles per hour?
in my opinion, if we wanted the exact number, we would have countless digits after the decimal point.
Yeah. Now we're going to get really nerdy here. You might think this is a totally, utterly pointless conversation or point that I'm about to make. But in terms of computers, it's not. At a split tiniest second in time, with our car, the wheels going roundy, roundy really fast, we could approximate that the speed is 50 miles per hour. We can get a little more precise and say that it's actually 51.0 miles per hour, because it was really like 50.6. So we'll call it 51.0. We could get even more precise and say, well, it wasn't 50 points. Oh, I did this backwards. I apologize. So there's the car going roundy, roundy. We could say, well, it's roughly 51 miles per hour. Well, we looked a little closer and we had a better sensor on the wheel. And it turns out it was actually going 50.6 miles per hour. Now, we got a new sensor with really, really delicate sensing, and it was, in fact, 50.600 miles per hour. Like, it was really wild. Like, the voltage was dead on the equivalent of 50.600 miles per hour. And we have some really sensitive equipment. And then some nerd comes along and says, all right, I have the most sensitive speedometer equipment that we can install on the axle. Let's measure down to the tiniest fraction of a voltage exactly what the speed was. And it turns out that this nerd says, well, listen, it was actually 50.600, and then 000. I'm going to write a ton of them. Two miles per hour. He says, no, really. The equipment we have is so sensitive and precise. They can measure the difference in voltage coming off of that wheel to that degree of accuracy. And at that point, if you have a speedometer that's digital and it's only capable of down to the 1/10 or point something, it would say 50.6 miles per hour. And it would be a lie. It wouldn't be true. If we were literally capable of producing some piece of equipment that could measure speed down to this tiniest fraction, well, now we have a digital machine that's saying, well, it's 50.6, and it isn't, because we don't have an analog to digital converter that has that level of precision. It doesn't work. So from one point of view, our digital machine, this speedometer, failed us. We're supposed to rely on it to give some indication of what's actually occurring in the real world. And from a certain point of view, it's inaccurate. But I use this rather extreme example to illustrate a pretty obvious thing. We don't care. Why? Because this is workable, and this is the point, and how we're going to go back to computers, for our purposes. The fact is that inside computers, we are going to be constantly trying to represent analog data, data that represents the real world in some way. We're going to try to represent that with some digital representation. And it's almost always going to be some slightest degree different from what actually exists in the real world. And that's fine. If we can represent it sufficient for our purposes, then these digital machines called computers work just fine. So to come back to these two different things, analog and digital. Here we have data that is a continuous stream of changing data of any possible amount. And here we have data, but it is a collection of individual data points or data elements that represent analog data as best as possible. With the allowed digits. So both of them represent data, but in analog, like a clock, like a speedometer, there's just a continuous stream of data being shown to you. It's constantly changing to some slightest degree or another. And that data can be any possible amount up to the tiniest precision that you want to look. Over in digital, we're still representing data, but what we have is a collection of individual data elements. They represent analog data as best as we can within the allowed digits. So what do we mean by allowed? Well, in binary, and we're not going to get into a bunch of nerdy binary math right now, you can represent whole numbers. We've done it a bunch. We had 4, 8 and 4, and 2 and 1, and we even had 0. But what we didn't do is talk about what do we do to the right of the decimal point. You can represent fractions. You can represent 2.1. You can represent 2.98 or 2.198 in decimal. You can represent 2.1984365.7. You can represent that. And depending upon your computer and how much memory you want to use, you can represent this all the way down to a significant level of precision. But at some point, you run out of memory and you have to decide what goes in this final box. And I remind you that while I've written this out in decimal, the actual numbers that we're going to store in individual pieces of memory are in binary. So when we store some information and look at the final box and say, well, we have to stop with our precision on this number. We don't have any more available room inside the computer, or we don't want to take up any more for our purposes. So where do we stop? And at that point, you've only got two options, a 1 or a 0. Now, in the real world, you might be representing something that in terms of its actual quantity is somewhere between 0 and 9, say. But you don't have those as available digits. You only have as available digits, because you're in a digital system, these two symbols. So we have to make a choice. And we have a little teeny algorithm that basically says, well, the analog signal coming in, if it's between 0 and 4, then make it a 0. If it's above that, make it a 1. And at that point, in this final little container, that's where our possibility of imprecision comes in. We had to make a choice. We couldn't represent the actual accuracy of the real world. Sorry. Couldn't happen. So why does this matter to us as programmers? First of all, are there any questions? I just went on some deep dive nerdy stuff. Any questions? Now, why do I care as a programmer? Can anybody think of any reasons why this should matter? Here's why. In our programs, we want to represent real world things. We want to represent students, or we want to represent products, values of physical elements. We want to represent things. We have to do so digitally. So let's say we're representing values. We're now talking about numbers. So let's say that the values that we want to represent are like for big, giant silos that contain wheat. And we want to record how many cubic meters of wheat are in there. And let's say these things are literally like 60 meters tall. And in diameter, they're like 15 meters. They're like massive silos. Now, we need to, in our memory, in the computer, in our RAM, we need to set aside some memory locations to store this amount. And if we want precision, like after the decimal point, we're going to need, depending upon how far, even more memory locations to store the data. So my question is, how many decimal points of cubic meter amount do you think we need Does anybody think we need any? Like, let's say it was 5,021.1 cubic meters. Is that a reasonable amount to store digitally in our memory? There's no right or wrong here. I'm just curious as to your thoughts. Let's take it the other way. What if we only had capability of doing it in hundreds? We only reserved enough memory to store it. How many hundreds? And there were 50 hundreds. Is that close enough? I mean, the exact measurement might be 5,021 point, say, 10379.265 cubic meters. If we were to go in there and count every single piece of wheat, is it okay for a program to only say that we have 5 times this many 100s? That's our accuracy, is the 100, because we only reserved a little teeny bit of memory. What do you guys think?
Depends. It depends on the value of the content.
Does it depend on the value or what we're using the value for? Let me just illustrate this. Let's say that this amount, whether it's 5,021 or whether it's 5,000, or whether it's literally 5,021.10379. All of these are some approximation of what the real volume is. But let's say we needed this number, whatever format we're all going to decide on. And it was for a company, some big limited liability company that owned 8,000 silos. And all they wanted to do was have some kind of a report that shows how many of their silos have wheat, how many have rye, how many have alfalfa, and what the total amount is. Over 8,000 silos. For that kind of a report, do you think we care about this degree of accuracy?
No.
What if there were literally, out of these 8,000, what if literally 3,500 of them had wheat? Does that 0.10379 really mean anything to us? Yes, no? What are your thoughts?
I mean, not really.
No.
Yeah, I mean,
It'll be
honestly,
less.
at the end of the day, frankly, we could call it 5,000 and we could be happy. If you are off by 21 across 3,500 wheat silos, okay, that's acceptable. That's acceptable. Now, what if, on the other hand, our computer program was going to be used to calculate how much of a special solution that was like some sort of like antimicrobial thing would be sprayed in there to stop mold? And it was, the scientists were telling us that they need to know down to the 1,000th of a cubic meter exactly how much wheat we have? Well, assuming that there are people that can measure that volume, we know that we need to store it with that degree of precision, which means we need to allocate a little bit more memory to have it that precise. So this is why it matters. Depending upon the context of the computer program you're building, you're going to need to make certain decisions about exactly how much precision is needed in the data you're working with. And understanding that you're never going to be 100% able to store in a computer what you can guarantee is absolutely accurate information. We start from there and we move backwards to, okay, we know we can never get it perfect. How much inaccuracy is acceptable for the given situation? What type of data do I have to choose that allows me to present or to represent data without wasting memory, without wasting the resources inside this machine? Because every time we add one more element of precision into the data we're going to store, there are costs involved. We need to take up that much more memory to store the data. And that's why I went into all of this, is because it's kind of interesting, I think, to know about like, oh, analog and digital. But what's more important as an engineer is to know that when you make choices about the precision level of the data that you're going to store inside the computer, or that you're going to, either temporarily while you're running the program, store it, or permanently store it on a hard drive, every single piece of data, the precision of it as it increases means more use of your memory. And that's a very real impact on your program. Any questions about that? All right, now that was way, way, way nerdy. Totally got it, okay? The big takeaway, don't ever forget about the impact of the precision of your data on your memory usage. And be cognizant of the fact that when you represent something that exists in the physical world, and you represent it in a computer, that it's never going to 100% reflect what that real world thing is. And you just need to get it close enough for your purposes. As long as it provides enough value and help to the users of your product, that's all that matters. Don't lose sleep over the fact that it's not 100% accurate. Okay. Enough nerdiness from that. All right, now we're going to switch gears entirely to this whole Boolean thing. Can anybody tell me who Boole, B-O-O-L-E, was?
He was like a mathematician or something.
Yep. How about Boolean logic? Anybody know what that is? All right, so let's look up some actual definitions here. One second.
When you say Boolean logic, do you mean like yes or no?
Yeah, it's funny. It actually kind of comes down to that, like to yes or no. That's really what it is. Okay. But let's look at some precision definitions. And I'm going to try to avoid Wikipedia just because they have so many confusing terms in their definitions. So what is first thing is that we understand what algebra is and what an operator is, okay? And by the way, the words here do matter. So what we're gonna do is keep track of words that we need to make sure we absolutely understand, okay? Here's the first one. Is anybody able to give a definition for algebra? It's pretty wild, isn't it? We all studied it. We all use it. There's not real awesome definitions for it. So that's the first thing we're going to look at, because it says Boolean logic is a form of algebra. All right. What is that simple Wikipedia called? Anybody remember what it is? It's called Simple Wikipedia. Eric, you're a genius. By the way, I use Simple Wikipedia like almost as much as I use regular Wikipedia, because it doesn't like overcomplicate the definitions of what you're trying to learn. Okay. So first of all, it explains what it means. It comes from Arabic. Reunion of broken parts. So this little sentence right here kind of puts a nail on the head. It's a branch of mathematics where we use variables to represent a value that's not yet known. And we could kind of stop right there and just let's just grab that right there. And there's a very specific reason I'm going to be this nerdy about it. Okay. As you're trying to read through programming tutorials and material on learning to program, they're using a few specific exact words that mean very precise things. And if you're not sure what they are, it makes it really, really, really challenging. So algebra is a part of mathematics. It uses variables to represent a value that is not yet known. What is implied here, we do know some data. That's implied. So where we have something we don't know, we're going to use a variable. There is something we do know. It's kind of implied. Would anybody question that implication? All right. Can someone give me an example of a formula that's algebraic that uses variables to represent a value that isn't known yet?
X squared plus x plus 1.
Give it to me again.
X squared plus x
Good.
plus 1
I don't know how to
equals
do
to 10.
I don't know how to do x squared, so I'm going to do a 2. Okay, because I don't think you can do it in here. Equals what?
10.
That is spot on. Good. So there's something we don't know yet, but there are things we do know. That is an algebraic formula. Good. Excellent. Now let's go back onto that definition here. Form of algebra centered around 3 simple words known as operators. What is an operator? Anybody tell me?
There's 6 operators, equals, no equal.
That's fine. What is an operator?
It's like a command which tells us what we are going to compute in mathematical expressions.
There we go. This says what we're going to do. An operator is an instruction. That's what the operator is. Okay, so we're getting closer. I think we should actually I should be better about this and copy down this, which is where we're coming from. Okay. So Boolean logic, form of algebra. So it's a part of mathematics where we use variables to represent values we don't know. And it's centered around some operators, some instructions. What are these instructions? They're right there on the screen. What are the three instructions?
And
Or and
or and not.
One of the first, and I know many of you have already seen these, but I just want to stress something. Those three words you see on the screen are a command. They are a thing to be done. When the computer sees those, it is being told to do a thing. So you can use them as verbs because there are things that can be done. You can or something, you can and something, you can not something. They are little instructions, directions. That fact opens up any sort of the most complex use of them that you can find. And there are sometimes quite complex uses of them. When you're looking at anything involving these three words, just recognize that you are looking at an instruction to the computer. If the computer reads those words, it knows, oh, there's a thing I need to do. Now, we need to look at another word. Can anyone here tell me what an expression is in mathematics?
Is a combination of numbers and variables.
Okay, we're getting close.
Which represents some value to be computed.
Now we're getting, okay, good. Okay, good. I like this. An expression is, let's simplify it, math work to be done. There's some math work that has to be done. Anybody dispute that or have a better definition? And I'm fine with this, by the way. It's not my strong area, although I know it pretty well. Okay, let's expand on this a tiny little bit. And you notice when we use the word math work to be done, there's a little more precise. Whoa. I don't know what happened there. The term is evaluated. When you evaluate an expression, that means doing the work. That means doing the computation. That's all it means. So this brings us to one of the central points about this Boolean logic thing. And this is this arrangement. You're going to see this all the time in one form or another. So let's look at this for a second. Can someone tell me what this means to do? What am I describing here?
You're taking one expression, comparing it to the other one, and then giving your result, yes or no, basically.
Yes. I want to use a little more precise terminology though. You said we're taking one expression and comparing it to another.
Mhm.
And in many ways, that is actually completely true, Jason. But let's use the terminology we have on the screen here. What we're doing is we are applying a Boolean operation to two expressions. So yeah, you're comparing them. You're right. But remember that up above on line 8, an operator is an actual thing that you do. There are a few different things you can do. They are, you can or something, you can and something, and you can not something. So we can talk about it as a comparison, and you're actually completely technically right, Jason. But I want to break it down to those 3 things. There are others, there's some nuance here, but these are the 3 that you're going to use a lot. So let's start to actually put in some real operators here. Let's put in and. What does this mean? I'm going to slowly introduce actual or like discrete real equations in here, but what are we doing right here on line 29? What does this mean to do? Anybody have any idea? Can you describe it in English?
There is a command called AND.
Okay.
It's an operation.
Good.
It operates on both the left and the right side expressions, which are called operands.
Good. Okay. Yeah, you get this is really good. Okay, good. Good. So
finally, after this whole operation, we would have a value. Specifically in here, it would be a Boolean value, true or false.
yeah, good, good. All right. So let's expand this a little bit. So we have a Boolean operator called AND. It's right here in the middle. There it is. Now, what does that command look like? Let's look at the command. Called AND. What does it mean to do? In plain English, what does this mean to do?
In order to be true, both values need to be true.
Good. In real English, it means something like this. Take in 2 values, each of which can be only true or false. Only output true if both of the input values are themselves true. That's what we're saying in English. Take in 2 values, and those values can only be true or false. Once you've taken them in, output a true if both the input values are themselves true, otherwise output a false. That's what it is in English. That's the command. The command says take in two values. That was spot on, Ellen. So now I ask you, if you have this equation right here, which you're going to use many times in programming, what order does the computer execute the different parts of this in? Or let's step back for a moment. How many tasks have we given the computer on line 29? How many things to do have we given it?
3.
Spot on, Ellen. Tell me what they are.
First, the computer will check the first expression to figure out if it's true or false. Then it
Yes.
will move on to the second expression, same thing, and then it will compare both to figure out if it's a real end.
Exactly. Even more precisely on that last part of the sentence, it would get done, evaluate an expression, figuring out what expression 2 ends up, and then it would apply the AND operation to both of those. There's nothing wrong with the way you said it at all. I just want to narrow in on the fact that that word "and," while they call it a comparator or a comparison, it's a specific exact computer operation you are telling it to do. It's totally fine to use the terminology you use, okay? So let's take this and now let's expand it a little bit more. Paste it. And let's say that expression 1, remember that an expression is a combination of numbers and variables, which represents some value to be computed. To get even more simple, it's just some math work that has to be done. Now, these expressions are very unique. And we can actually expand a little bit. Expression 1 and parentheses, answers are only true or false. There we go. So there's another reason why I've been trying to have you not so much use the compare word. And the reason for it is I want to expand what this expression is. Expressions, these are comparisons. That's where the comparison is. Now, what are the comparators that a computer can use?
Is it lesser, greater, lesser or equal, greater or equal, and equal, different?
And then there's not equal. I don't know. I forget what's the 2-stroke combination for not equal? Oh,
exclamation.
bang, equal. Yeah. Now, here's the thing I'm trying to stress. These comparators have been around since people like civilization started. Whatever the words for them, these are almost intrinsic in human civilization. You might have a specific name for them, but we all understand the concept, and they are in fact built into digital computers. what part of the CPU can perform these comparison operations?
The ALU.
Exactly. The arithmetic logic unit can do these 6 comparators. So part of the reason, again, that I was harping on not describing this middle thing, the Boolean operator, as a comparison, is that's not actually where the comparison occurs. Comparisons occur in these 2 expressions on either side. And when you're reading any sort of like, education material about Boolean operations, if you read the word comparison, and of course, if it's being used properly, and think that it applies to this middle part, you'll get pretty confused. Comparisons happen on either side, because comparisons, if you look at these, only have one of 2 possible outcomes, true or false. As we're going to see, these operations do not have one of 2 possible outcomes. Most of them have 4 possible outcomes. Now, they're made up of those 2 values. There's some semantic nerdiness going on here, but it does matter in the long run. So just bear with me. All right, so we have these comparators. Where are the comparators used in this original equation? Where do we use those?
In the expressions.
Exactly. So we could actually say expression that uses a comparator, number 1. And on the other side of it is an expression that uses a comparator, number 2. And in here is, oh, I should have put that up here. In the middle is our Boolean operator. Now we're getting even more precise. This is Boolean logic at work inside a computer program. You will, depending upon the operator, but almost in nearly every case, you'll have some work to be done. Ellen called this spot on. We need to do the actual work before the operator, the first expression. We need to do the work after the operator, the second expression. Both of those are going to have only one of 2 possible outcomes, true or false. Once we've done that work, only then can we actually run an operation against them. Which brings us to the final thing we're going to talk about, and then we're going to end off, which is called truth tables. Can anyone tell me what a truth table is?
The true and false values of their different combinations.
Good. Okay, we're on the right track. This is a table showing the operation. Nice, Eric. Of a particular Boolean operator. Remember that an operator is an instruction. So here's an instruction. We have 3 major operators. What are they again?
And or not.
Good. So let's see if we can actually show how they operate. So we said this command called and was to take in two values, each of which can only be true or false, and only output a true if both input values are themselves true. Has anybody in the class ever drawn up truth tables before?
Yes.
Good, you have it, Ellen. Anybody else?
Yes.
Good, excellent. All right, well, what's been, let me go and pop this up. Raise your hand if you have not written down truth tables. Jason, Alexandra, Sudesh. Okay, good, totally fine. I'm going to show you one of them, and then for your homework, knowing what they are, you'll be able to look up some others. Now, remember, we said that a truth table is a table that shows how a particular operator works. And this is how a Boolean operator works. We're going to look at the truth table for this Boolean operator, which is an instruction. How do you and something? I love using it as a verb. I'd like to and something. What you do is you look at what is being input. You have two inputs. And then once we do the work, what do we output? It's right here that the work gets done. Let's say we input a 0 and a 0, also known as a false and a false. The way it works is you're only going to output a false, a true, if both the inputs are true. Are any of these inputs true? Are any of them 1? No, so you put a 0 out. What if the first input, we're going to call these A and B just to differentiate. What if this first input is still false, but the second one is true? Can we output a true? Nope, they both have to be. What if that second one's true and the first one's false? Or sorry, other way around. What if the first one's true, second one's false? Nope, they both have to be, so it's still, when we do the work, we output a false, a 0. And what if they're both true? Then we output a true. Now, I want to stress again that we don't even get to the point where we can do this operation, which I am making this huge, ugly, solid line. That's where the operation is. We don't get to do the actual operation until we know what these are. And we don't know what they are until we've actually done the expressions. Again, it looks like this. Expression 1 is here, and then the Boolean operator, BO, and then expression 2 is here. We can't do this until we actually know whether we have a true or false on either side. And that's why Ellen was spot on. Evaluate the expressions first, and then apply an actual operation to them. So this is called the truth table right here. For all the varieties of input, what do you get as an output? So we're going to end off right there because we've gone to our 9:30, okay? And your homework is really, really simple. I want you to write up the truth tables for and, or, and not. If you want extra credit, then look up a few more of these Boolean operators. Remember that they are in fact commands and instructions, and write up the truth tables for those. But be prepared to explain them if you do that extra credit, because I'll probably put them on the screen and have you talk about them. So that's our class for today. Questions? Okay, cool. Now, we started out really nerdy and with this analog to digital thing, which is rather esoteric and not that applicable to day-to-day programming. but then hopefully you start to see some of the value of understanding the trade-offs in how much space you allocate for storing information digitally. The more precision you want, the more of an impact on memory. And you can try to be as precise as you want, but you can never 100% guarantee you'll represent the real world. And finally, this stuff, this is the bread and butter of a lot of your programming, is understanding the difference between an expression and a Boolean operator. Now, if we go back here, remember that the expression is math work that needs to be evaluated. That's a very general term. A Boolean expression, so a comparator expression, only ends up being true or false. Other expressions can end up being like the number 42 or whatever. It's just math work. These comparisons are, where are they? Sorry, these expressions use a comparator. So this right here is the most important thing to think with as you start building out your programs. We will come back to this over and over and over and over again as we build out programs. Okay, cool. That's it for the day. Send me send me your answers about whether you are okay with going a little bit longer, like another half hour on these classes, but send them privately to me in Discord. I would prefer that. And we'll make some decisions about that in the next day or so, and I'll let everybody know. That's it. Thank you guys so much for your involvement. Appreciate it. If you're watching this now or in the future, we're getting farther and farther into the fundamentals, and it won't be very long before we start laying down how to design programs and start actually coding. We're just putting some more of these fundamentals in. Any questions?
Nope,
right.
thanks.
Thank you guys. I'll continue evaluating the homework. There's a couple people I still have yet to respond to. And I will see you all tomorrow. Same bat time, same bat channel.
Thank you. Good night.
Yep.
Thanks.
folks.
Thank you.
Bye.
See you, everyone.